All right, well, hello everyone, and welcome to our lecture number 1. So this is a review of electrical quantities. And so first, let's just start with why we're actually here. This is circuits for engineering majors, so why should us engineers take circuits class? And this MIT professor, Steve Centuria, gave a really nice definition. He said that engineering is the purposeful use of science. And so let's just keep this in mind as we go through this current lecture as well as the future ones, that really at the end of the day, our goal is to apply principles of circuits and devices to do useful stuff. And if we look around every day, you see circuits are everywhere. And especially those of us going into engineering and computer hardware, computer science, we are always needing to work on electrical devices. And so let's keep these applications in mind that, there are certainly going to be times when we need to operate, manipulate, troubleshoot devices. There's definitely going to be times when we'll be using electrical phenomena, for example, for things like sensors and touchscreens. And another interesting one is use of circuits as a model for other systems. And if you are into bioengineering or civil engineering, for example, you might see that electrical circuits are an excellent model for mechanical systems like pumps, as well as the human circulatory system. In fact, they actually often model the human heart as a voltage source, and then you have the different arteries, blood vessels in your body that act like resistors or other components. So let's keep these applications in mind, and throughout this class, we'll keep reminding ourselves as much as we can about why all this stuff matters. All right, so you may remember from prior coursework that the water analogy is a very common model used to help visualize an electric circuit. So in the next few lectures, we'll occasionally be looking at this model to help us visualize what's going on. So you remember, in an electric circuit, the thing that's actually flowing is charge. So electric charge in a circuit behaves a lot like water in a mechanical system. So for example, here we have this dam, right? It's like a hydroelectric dam, and there's some water over here. You can see that we have water flowing and we see that water flows from areas of high potential or high pressure to areas of low potential or low pressure. So in a mechanical system, water might flow from high elevation or high pressure to low elevation, low pressure. Similarly, electric charge flows from areas of high voltage to areas of low voltage. It is a voltage difference that causes water, or in this case, electrical charge, to flow. So please remember, charge is the thing that's flowing in our circuit. And of course, that's the fundamental property of matter. Things may be positively, negatively, or neutrally charged. And then voltage, of course, is that potential difference which causes charge to flow. Next, we have current. So current is the flow rate of our water in a mechanical system. In an electric system, current is the flow rate of charge. So the units are actually charge per unit time. And of course, you might remember that the units of current are also given in amperes. So we'll cover that more later. So here you see the current is however much charge is flowing at a given amount per time. Resistance is resistance to flow. So of course, in a mechanical system, that might be friction, but in an electrical system, resistance is resistance to flow of charge. Next, we have work. Work is very important. Work is basically how much force is being exerted by my current, right? How much force is being exerted by this current that's flowing. How much pushing force are we pushing? In this case, on the water wheel. In a circuit, how much electrical work is being done on a circuit element. So that's the pushing force we are able to exert. Most often, the property we care about even more is power. That is work per unit time. So you might remember power has units of watts or joules per second. Work would be joules. Often we care about power because that is how much work we can do per unit time. And finally, another very important property is energy. So energy is the total amount of work that is done over a given amount of time. So if this water wheel's been spinning for a while, how much did we charge our batteries? How much energy did this flowing water produce? Make sure you use this water analogy to help you visualize what's going on in circuits, and you'll see we'll return to this water analogy from time to time to help us understand what's going on. All right, so let's go through a few more key terms and variables to help us all get on the same page about circuits. First, electric circuit. An electric circuit is an interconnection of electrical elements linked together in a closed path so that an electric current may flow continuously. So notice that in this case, this sample circuit shown here, there are only closed paths. There aren't any, there's no open section here. We don't have any of that. In this case, the circuit, it has a bunch of interconnected paths and current is flowing. Next, there's an element. An element is a piece of an electric circuit. So, for example, the batteries, these sort of blue boxes, these are elements. So, a resistor, source, battery. Another important circuit term is nodes. A node is a place where different elements are connected. And the voltage at a given node is constant. So this whole area here is sitting at the same voltage. This whole thing can be considered a single node because that's where these sort of element 1, 2, 3, these are all connected to this top node. Similarly, there's another node down here and a third node over here. We'll return to nodes in a couple more lectures and we'll see that they're actually very useful for us for solving different types of circuit problems. All right, so next, let's go into a little more detail about each of the terms we just covered. So if we revisit from before, we first have our term charge. Charge is an intrinsic property of matter, and again, it is that quantity of electricity responsible for the behavior we see. So matter has positive, negative, neutral charge, and this is the thing that makes circuits actually do their thing. So charge, the symbol for charge is Q, and units typically are coulombs. And a single electron, just for fun, a single electron has a charge of 1.602 times 10 to the minus 19 coulombs. So 1 coulomb is actually a ton of electrons, over 10 to the 18th electrons worth of charge. Next we have current. Current is the time rate of flow of positive electric charge. So symbol for current is letter I. And notice units here are amperes, where 1 ampere is 1 coulomb per second. So current is how much charge flows per time. Notice here we wrote that current is the time rate of flow of positive electric charge. So we have some fine print down here. Remember that by convention, we say that current is flow of positive charge. So electrons are actually flowing in the opposite direction as conventional current because electrons are negatively charged. How about another fun fact? So for batteries, for example, if you look at a cell phone battery, a laptop battery, charge is sometimes written in ampere hours or milliamp hour units. And so 1 ampere hour means you can deliver a steady current of 1 ampere for 1 hour. So there are 3,600 coulombs per 1 ampere hour. So let's continue our list of terms. So next important term we have is DC and AC current. You may remember from prior courses, DC current is current with a constant magnitude, so it does not change with time. AC current is alternating current, or current with a sinusoidal magnitude. And so, in fact, alternating current, sometimes it can even change directions at different points in time. For now, we're going to focus on DC current, but we'll return to AC current a little later in the class. All right, so now comes the fun part. We talked about current, charge, voltage. How do we actually calculate these things? Well, it turns out that there are some nice mathematical relationships we can use. Remember, we said that charge per time is current. And so if we know our charge, Q of t, we can find current I of t by taking the derivative. That's not so bad. So if we know charge, we know letter Q, just take the time derivative to get current. Similarly, we can go in reverse. If we know current I of t, and we want to find how much charge was delivered, then we just take the integral. So in this case, charge is just the time integral of our current. So make sure you know these relationships. You might see they're often on homework and even on exam questions. And of course, I'm not going to expect you to take crazy derivatives and crazy integrals, but if you pay attention to the examples that are given in these slides, you'll see that you should still know how to take derivatives and integrals of basic quadratic or exponential expressions. So, make sure if you're a little rusty on derivatives and integrals, might be a good idea to review derivatives and integrals of polynomials and exponential expressions. Those are the ones that come up most often. Okay, so now let's go ahead and move on to voltage. So voltage is the amount of work required to move a unit positive charge from the negative terminal to the positive terminal. For me personally, I prefer a picture, so I came up with this cheesy illustration down below. And you can see basically if this is me trying to push a unit positive charge up a hill, voltage is basically like that. We're trying to push something uphill against the normal direction of flow. But if we want to make that charge go toward another positive point, we're going to have to apply energy to make this 1 coulomb charge go against its desired direction. So voltage is that work or energy required to move this 1 coulomb positive charge uphill from the negative terminal to the positive terminal. So mathematically, we write our voltage as derivative of work with respect to charge. Symbols V for volts, units are volts. And notice the convention here. A charge of 1 coulomb delivers 1 joule as it moves through a 1 volt voltage. So as seen in this picture, if I move my 1 coulomb charge from the negative to the positive, if it drops this distance of 1 volt, then we see we will deliver that energy of 1 joule. All right, so now let's talk power. Power is, by definition, the time rate of supplying or receiving energy. So mathematically, energy per time or derivative of work with respect to time. Symbol for power is P, and the units are watts, where 1 watt is 1 joule per second. And so, also very important to note, we can show that power is also equal to voltage times current. So we use this relationship a lot. So remember, if you know how much voltage is traveling across an element and how much current, then you can find power. And of course, the units here are volts, current is amperes, and power is watts. Okay, next one, energy. Energy is very important. Energy is how much power we can supply or receive over a given time. So, for example, in this case, how much can we charge these batteries using our spinning water wheel? So, symbol for energy is W, and the units here are joules. And to find energy, all we need to do is take the integral of power. Because remember, energy is basically power times time. Power is joules per second times time, which is seconds. So make sure you remember this relationship. From time to time, there may be homework or exam questions that ask to calculate energy. So make sure you remember, in this case, joules or seconds or watts times seconds will give us energy. Another fun fact. Often we see energy, like on your electric bill, written in kilowatt hours. And so 1 kilowatt hour is 1,000 joules sustained over 1 hour. All right. So next, let's talk conventions. Here are some important conventions that we're going to use for this class. First, we have our friend Benjamin Franklin, who introduced that electrical current is the flow of positive charge. So remember, electrons are negatively charged. So in this class, when we talk current, we are actually talking about flow of positive charges. Electrons are actually moving in the opposite direction. Another convention, we use a lowercase letter to denote variables which are functions of time. So for example, here charge Q of t, lowercase q means charge is time dependent. And finally, we use an uppercase letter to represent a constant value. For example, big Q here, capital Q, this means a constant charge. So in this case, constant charge is not changing with time. So often a lot of textbooks will use this convention, so just be aware, little q or lowercase letter will be for time-dependent quantities, capital letter for non-time dependent. All right, finally, a couple other things that we definitely want to know. Definitely make sure you know how to use our favorite systems of units. And so these are the big quantities that we will be using most often. So remember, of course, charge units are coulombs, current is in amperes, voltage is in volts, resistance is in ohms. Definitely get to capacitance and inductance later, and conductance is the opposite of resistance, or inverse of resistance, and that is in Siemens. So these are the most common units that we run into in this class. All right, next is SI prefixes. So I'm not going to expect you to memorize all these different prefixes, but they will come up in various homework problems and practice problems. So be aware of these prefixes and make sure you know what they mean if you see them. Especially be careful of milli versus micro. This is one where some students sometimes get a little bit confused. Remember, milli is 10 to the minus 3 or 1/1000th. Micro is 1 over 10 to the minus 6 or 1 divided by 1 million. So make sure you don't confuse those two. Milli and micro do come up fairly often in this class, as well as kilo for 1000. All right, so that's enough of me talking for now. Let's go ahead and try a quick question. And so if you're following along with the video, I'd encourage you to pause the video for a moment and think about which of these circuit elements is absorbing power and which of these circuit elements is emitting or supplying power. Just based on what we've covered. It's okay if you're not sure, just think about it for a moment and think about how might you be able to tell whether either of these elements is absorbing or supplying. Take a moment and think about it. And when you're ready, please go ahead and continue the video to the next page. Okay, well, often when students see this question, it's kind of a 50-50 split between choice A and choice B. Some students think element A is absorbing, B is supplying, and some students think the opposite. But here's a secret trick. When in doubt, draw a picture. And you'll find that drawing a picture can actually be very helpful for sort of thinking through these types of problems. And so in this case, here's a picture that you could draw. Notice that in circuit element A, I'm going from positive to negative voltage. So this is an area of higher potential to negative, which is an area of lower potential. And my current is entering the positive terminal of element A, so that means I'm starting at a higher potential and ending at a lower potential. So this is similar to water flowing downhill through a water wheel. So notice in the case of element A, we see that we start out with high potential and we end at low potential. And the water wheel spins. So in this case, our water wheel is absorbing energy. Right? It's absorbing some of that energy from the current flowing from high to low. So in this case, element A, we can say, is absorbing power. Now let's consider element B. And you can see that element B is a little bit different because our electric current here is entering an area of low potential. And then our current exits at higher potential. So in this case, the water is flowing uphill, or our current is flowing uphill. In this case, element B must do work. To push our current uphill to higher potential. So notice in this case, element B is supplying power. See the difference there? So if we kind of draw a picture and visualize, we see that element B has to supply power to the current in order to push it to higher potential. Just like I'm trying to pump water uphill. Meanwhile, in element A, we saw the opposite was true. Our water, or our current, was flowing downhill to lower potential, and this caused our element A to absorb power. So this water wheel analogy can be really helpful. It's a little bit cheesy, but I found that it's very helpful to students to think about this water wheel analogy. This can often be very helpful to determine whether a circuit element is absorbing or supplying power. And so, in fact, there's actually a technical term for this. So the water wheel analogy, that's just a cheesy thing I made up. Our textbook calls this thing the passive convention. So the passive convention is used to determine whether we are absorbing or supplying power. And so here's the deal. So for the passive convention, in order to satisfy the passive convention, current must enter the positive voltage terminal. So for example, if I have some element, then current must enter the positive end. If the passive sign convention is satisfied, so if current is entering the positive terminal, then we can say if our power is positive, we are absorbing power. If our power is negative, that means the element is supplying power. So that's another way to determine whether you're absorbing or supplying power. If we apply the passive convention to element A and B, you can see we get the same result as before. For element A, passive convention is satisfied, and power would be current times voltage. We would get a positive number because both of these have positive sign, and so we could say that we are absorbing power. However, for this second one, element B, we see that the passive convention is not satisfied, so that means in this case, element B must be supplying power. All right, let's try some practice. So here we have 4 circuit elements, A, B, C, and D. Our goal is to find which of these supply 12 watts. And so take a moment, pause this recording, and see if you can find the correct answer. Okay, so let's go ahead and talk through this. There's 2 ways to approach this problem, and one way is to use the water wheel. So we can draw a picture and see whether we are flowing uphill or downhill. And we see, for example, with element A, that we're flowing from positive to negative voltage. So in this case, we know that element A must be absorbing because in this case, that water wheel has to be taking some of the energy. So one way to solve this problem is to go through and just use water wheel. And we see, for example, element A must be absorbing. And similarly, element B, since we're going from negative to positive voltage, current is entering at the negative end, we see that element B must be supplying, because element B must exert some energy in order to push our current uphill. Another way to approach this problem is just to look at passive convention. So remember, to satisfy passive convention, current must enter the positive terminal. So if current enters the positive terminal, then positive power is power absorbed. Otherwise, if current does not enter the positive, if current enters the negative, then positive power is power supplied. So in this case, we see for element C that our power is 6 volts times 2 amps, 12 watts, but since current enters the negative side of element C, this is supplying 12 watts. And then finally, for element D, we see current enters the positive end. So our power is 3 volts times 4 amps, 12 watts. And because current is entering the positive end, that 12 watts must be absorbed. So either the water wheel analogy or passive convention, either of those approaches would have been valid to solve this problem. Okay, let's try one more just for fun. So kind of hinted at it before. Follow-up question is asking which of these absorb 12 watts? You can pause the video and think about it. All right, and we hinted at this one before, but we found from our last question that B and C are supplying power. And we'll see in this case, element A and D are the ones that are absorbing 12 watts of power. Okay, so our last new topic for today, before we do examples, is to just cover two more basic terms: analysis versus design. So when we say circuit analysis, what we mean is we are studying a circuit to find unknowns. Analysis is all about finding unknowns. Meanwhile, design is the process of creating a circuit to satisfy requirements. So design is a little bit more of that sort of engineering, optimizing. We're trying to satisfy requirements. So you'll see in this class, we're actually going to be doing both of these things. So let's spend the rest of our time today doing a few examples. Let's start with example 1. And feel free to follow along on the reference handout if you have it available. So in example 1, we're being given the total charge in a circuit element. And so here, let's just assume this is charge in coulombs. So we're given charge in coulombs. And we want to find our current I of t. And in this case, let's find it in amperes. So we're given charge, or Q. We want to find current I. So think for a moment, how might we approach this? Do we have some relationship between current and charge that we could use for this question? How is current Q of t related to I of t? Take a moment and think about how you might approach this problem. Go ahead, pause the video if you need, and when you're ready, let's talk through it. Okay, so let's go ahead and give this a try. You might remember our current I of t is given by the time derivative of current. And we know Q of t. So all we need to do here, let's take the derivative of Q of t. So let's go ahead and give this a try. If you'd like, consider pausing the video and mathing it out yourself. And I'll go ahead and do it on the next slide. Okay, so I'm going to go ahead and take the derivative. So in this case, I want to take d dt of I have 1.25 times 1 minus e to the negative 5t. So I'm just going to distribute my 1.25. So distributed that through. And so now we know that the derivative of a constant, d dt of 1.25, that's just going to be 0. And then similarly, we want to take the derivative of that exponent. So that basically, we just move the negative 5 in front. So this becomes negative 5 times, in this case, it would be negative 5 times 1.25 e to the negative 5. t. And so be careful here of potential sign errors because you don't want to accidentally create any issues there. So notice we're subtracting, pulling -5 in front, and then we still have the minus 1.25 e to minus 5t. And so if we go ahead and math that through, that will give us 0 minus negative. We have 5 times 1 1/4. That gives us 6.25 e to -5t. So minus negative, that becomes a positive. So I of t will be 6.25 e to the minus 5t. And our units are amperes. And of course, notice this is for time t is greater than or equal to 0 seconds. So there you have it. Make sure you remember how to do these derivatives of exponential expressions, as these do come up from time to time in the class, and similar questions like this have appeared on past homework or exams. All right, let's try one more. So again, there's a solution. If you're curious, you can pause the video, take a look. Let's try one more example. So here we have the current in a circuit element. So we are given this expression for I of t. So we have kind of this whole relationship. And we want to determine how much charge flowed through that circuit element between 400 and 800 seconds. So how much charge flowed during this time? So again, between 400 and 800 microseconds. Okay, well, take a moment, think about how you might approach this problem, and then let's discuss it. Go ahead and pause the video if you need. Okay, well, let's talk through this. Notice that we know that our current I of t must be 720 nanoamps during 400 to 800 microseconds, right? We know that the current is constant at that point. And we also know that Q, charge, is just going to be the integral of current. So in order to find charge, we just have to integrate current. So if you'd like, go ahead, pause the video, see if you can do the integration, and then we'll go ahead and do it together. Okay, so let's go ahead and give this integration a try. So here we know that our current I of t is 720 nanoamps, or 720 times 10 to the minus 9 amps. I'm going to proactively convert to amperes to avoid unit conversion errors. Because notice this is nano amperes. Okay, so I know my current, and I know that my charge is equal to the integral of I of t. But in this case, I just want to integrate from 400 microseconds to 800 microseconds. Or if I want to rewrite that in terms of regular seconds, that would be 400 times 10 to the minus 6 seconds, 800 times 10 to the minus 6 seconds, and my I of t is 720 times 10 to the minus 9 dt. So this isn't a bad integral. All we need to do is integrate a constant, so therefore we get that our q of t is just 720 times 10 to the minus 9 t, and we substitute in 400 times 10 to the minus 6 seconds and 800 times 10 to the minus 6 seconds. So therefore, our charge q becomes, in this case it's not q of t, it's just our regular q, it becomes 720 times 10 to the minus 9 multiplied by 800 times 10 to the minus 6 minus 400 times 10 to the minus 6. And if we math that through, we determine that our total charge q from 400 microseconds to 800 microseconds is going to be equal to 2.88 times 10 to the minus 10. And what's our units? Units of charge is coulombs. Again, because here we have amperes, which is coulomb per second. And then we have, amperes is coulombs per second, and then here we have time in seconds. So you want to be careful here. Notice that I did convert my units into amperes and seconds so that I could end up with coulombs. If I had left everything in terms of nanoamps and microseconds, I would have gotten an incorrect answer because I had not had everything in terms of amperes and seconds before getting my coulombs. So pay attention to those units as well. All right, so let's go ahead and move on to our last example for today. So this is example 3. Here we're given that we have a lightning bolt. And so our lightning bolt gives us a current I of 20,000 amps. And what else do we know? We know we have a 0.1 second duration. And we know that our voltage between the clouds and the ground is 5 times 10 to the 8 volts. So we're being asked two things. First, how much charge is transmitted by the lightning bolt? And second, find the energy released. So take a moment and pause the recording if you'd like. Think about how you would approach this question. When you're ready, we'll go ahead and discuss. Okay, so let's first think about total charge. Let's remember that current I is, in this case, 20,000 amperes, or 20,000 coulombs per second. And we also know that our time t is 0.1 seconds. So if you caught on that this was a constant current for 0.1 second, you could simply say that total charge is current, or coulombs per second, times time, which is seconds. Seconds cancel, and then we would be able to find our charge. So in this case, one approach would be to take our 20,000 amps, which is 20,000 coulombs per second, times 0.1 seconds, and notice that gives us 2,000 coulombs. Another approach would be simply to use that classic integration approach where we know Q is equal to the integral of current. So similarly, you could say that our charge Q would be the integral from 0 to 0.1 of our 20,000 dt. And that would also give you Q is 20,000 times 0.1, or 2,000 coulombs. So either approach would work. Either approach gives you the correct answer. So now let's think about part B. Find the total energy released. Think about how you might solve that, and then we'll go ahead and discuss. Okay, so let's remind ourselves. Energy, remember energy W, that is just the time integral of power. And remember, power is equal to current times voltage. So we can also write that energy is equal to V of t times I of t. What do we know in this case? Well, we know V of t, that's 5 times 10 to the 8 volts. We know I of t, that's 20,000 amps. And in this case, we know that our time t is 0.1 seconds. So all we need to do here is plug and chug in order to find our energy. So here, let's go ahead and plug in our voltage and our current. And we determine, in this case, our energy is the integral from 0 to 0.1 seconds of 5 times 10 to the 8th volts times 20,000 amps. And if we math that out, we get the integral from 0 to 0.1 of 10 to the 13th. And so, therefore, we determine our energy is going to be, in this case, 10 to the 12th joules. All right, so hopefully by now everybody's getting a little bit more comfortable with these electrical quantities. Definitely a great idea to review basic derivatives and integrals, basic SI units, and also make sure you get comfortable with the relationship between energy, power, voltage, and current. These are very important quantities that we'll continue to revisit throughout the semester. All right, and again, there's a cleaner solution if you'd like to review that. And so that's it for today. So thanks everyone for joining the fun, and hopefully now you're able to better understand why we should care about circuits in the first place, and remember these key electrical circuit quantities that we're going to use in the class. So thanks everyone, and we'll see you in the next video.